Welcome to our lectures on DC microgrid and control system. Today we shall discuss about microdynamics of this microgrid dynamics and its modeling. So, our content of this today's lectures will be dynamic modeling of AC microgrid, what we require to understand, because there is some portion of the microgrid might be the DC. So, we shall also take the modeling of the AC microgrid, and then we shall see that what are the changes of the AC microgrid and the DC microgrid. So, voltage controlled voltage source inverter, we shall see that how it will be designed. Thereafter current control voltage source inverter, and then control objective of AC microgrid will be discussed. Now, as we understood that the microgrid control scheme employs nonlinear dynamics model of the distributed generation. These are solar cells, micro turbines and wind turbines. And in this lectures we shall consider dynamic modeling of voltage control voltage source inverter, that is in abbreviation we shall use VCVSI. And also this is another inverter will be used also, that is called current control voltage source inverter. So, all will be the voltage source inverter. As you know that if it require to be the current source, we require a constant source current, but there is a problem of availability of constant source current. So, we shall see that what are this among this, which one will be preferred and why, and how we require to model it. Each inverter is modeled on the individual reference frame whose rotational frequency is set by the local power sharing controller. So, it may be something that you have a different microgrid and they are not very fixed on the voltage regulation part. Like we have a organization like Power Grid Corporation that fixes up the whole India to have a 50 hertz frequency, but you can have a small microgrids and which having it is old frequency within a limit of operation, and it is set by the local power sharing controller, that is kind of off grid kind of system. The inverter module includes power sharing controller dynamics, output filter dynamics, coupling inductor dynamics, voltage and current controller dynamics, and list the two equivalent these last two equivalent elements, that is introduce high frequency dynamics which are apparent at the peak and the light load conditioning during the load change. Let us explain it what it is basically. So, coupling inductor dynamics is something that it has, when it is loading, generally frequency will have a roll off, this inductance value will come down, and so we require to take a precaution of kind of inductor you are designing. And voltage and the current dynamics also will change if the parameters like the inductor changes. So, in light load and full load these characteristics will be different. Now, this is the block diagram of voltage control voltage source inverter. You will have a voltage controller, so that will control the terminal voltage of the inverter, and it will take input from this VOI as well as IOI, and ultimately it will check the frequency as well as the terminal voltage or the required voltage to be connected to the grid side, and thus you got a power controller, and thereafter it will feed input to this in DQ frame, that is VDO I and VQI, and thereafter it will be feeding to this controller. Then also you will be feeding the controllers of this is the reference output voltage and output voltage in the DQ frame. This is the actual VDVQ output voltage that you are injecting in the grid or the microgrid or the point of common coupling, whatever it may be, and this is the current that is you are injecting also at the PCC, and accordingly voltage controller will generate the reference for the current, that is IL D star and IQ D stars, and they will have a current controller, and this current controller will actually have an inner loop, and it will be a faster loop because it will work on a switching frequency, and voltage controller will be a slower loop, and its bandwidth will be 10 times less than this bandwidth, and so you can have a ABC to TQ transform and you will inject the power to the grid. This is the control block diagram of inverter based DG system. Mostly in case of the solar inverter, you will see this kind of control structures. The block diagram of this voltage control voltage source inverter is based on DG is shown in distributed generation, is shown in figure 1. It contains the inverter bridge connected to the primary DC source. It can be solar photovoltaic cell or it can be a fuel cells. The control loops including power, voltage and the current controller adjust the output voltage and frequency of the converter. So, you will have a reference frequency and reference terminal voltage that required to be maintained in injecting it. Given the relative high switching frequency of the inverter bridge, the switching artifacts can safely neglected by the average model. So, we shall consider, so there is two state, one is switching on state and switching off state. So, all those parameters will be having, we consider that average model, and it should be noted that the nonlinear dynamics of each distributed generations are formulated in its own DQ reference frame. So, there is a sending in a different reference frames, PI controller tuning become easier because this quantity looks like DC in the DQ domain. And suppose that the reference frame of this ith DG is rotating at a frequency of omega I, the reference frame of the DG is considered as a common reference frame with a rotating frequency of omega com. So, we can have a difference of this thing. So, ultimately whole systems required to be synchronized, that is a challenge. Sometimes we may have a little frequency difference, and the angle of ith DG reference frame with respect to the common reference frame is denoted by delta I and satisfies the following relation, that is basically delta I dot should be equal to delta I minus delta com. So, the power control block, that is the power control block which was been shown here also, this block essentially. So, the power controller block which we have shown there, it has been represented here. So, it has the output voltage and output current as an input, you convert to ABC to DQ frame, and thus you got this all the quantities in VDQ and VDQ and VD and IDQ and ID. Thereafter, you have a real power in a DQ domain, that is VDID plus VQIQ, and the cross product, this is basically the imaginary power or reactive power. So, that is VDIQ minus VQID, and thereafter it will be passed to the low pass filters. This will actually require to control the frequency. So, you have a reference frequency, ultimately it will see that whether it is having that droop control or not. This will ensure that this frequency has been maintained by these methods, and you get QY essentially the reactive power and the terminal voltage, and from then actually you will have reference ODI. So, and your VQI with respect to it required to be 0 because your power factor required to be unity. In that way essentially you will operate. So, let us describe it. The power controller block as shown in the figure 2 contains the Drup technique, and that is the Drup equation for Drup technique, and provides the voltage reference for Vd star di and the Vq star di for the voltage current as well as operating frequency omega I for inverter voltage, where E star and omega star the primary control reference of the distributed generator output voltage RMS value and the angular frequency at the no load conditions with respectively, and dP and dQ are the Drup coefficients. The low pass filters with the cutoff frequency omega I are used to extract the fundamental component of the output of the active reactive powers, denotes the Pi and Qi respectively. It may be so that this system has a harmonic, so it will have a harmonic powers. So, once you pass through the low pass filters, this harmonic power gets eliminated, you have a average DC power. So, if you differentiate this equation Pi, the power real power equations, you get omega Ci Pi, because it is and plus omega Ci into the real power. Similarly, if you differentiate the reactive power, then you get minus omega Ci Qi plus omega Ci of this R, and this one is again P and this one is again Q. So, where VDI and the VQI, ODI and OQI are the direct and quadrature axis of the VOI and IOI, and this figure 2 we have seen that the primary voltage control strategy for the each distributed generator aligns the output voltage magnitude to the D axis to the corresponding reference. So, that you have aligned your A axis with the D axis and you have a unity power factor operation, and thus this is the Drup. ODI should be E minus dQi into Qi, and this should be equal to 0. So, voltage control block diagram of the inverter. Now, essentially what you have seen in the first figure, please go back, or you can turn your lecture. Ultimately, this we are going to discuss this. So, let us see how it will work. So, you got the reference ODI from this previous equations, and you have actual VODI. So, you will subtract it, then you will put it to the PI controller, and this component should be DC in the DQ domain. Thus, tuning of this parameters in DC is easier, and for this reason we prefer to work into the ABC instead of ABC, we work for the DQ frame. So, then you got essentially the VQI, and output of this thing will be the current, and you will sum up the current for the filters, that is OQI base frequency to CFI, and similarly ODI into FI. Ultimately, this will give you the direct access reference current. Same way, ideally this value should be 0. So, this value will subtract, you will fade with compare with this Pi, and you have ODI plus omega CFI, it has to be add up this part of the current, and thereafter you will have this frequency into A, and ultimately you get the IQ reference. Now, CFI is which filter? Let us see this block diagram, then only you will understand. CFI is this filter. So, this is the overall block diagram to generate the reference ID star and the LD star, IQ star and the ID star. The differential algebraic equations of the voltage controller can be rewritten as, this is a flux differentiation of the flux gives us the voltage. So, for the ith generator, in d axis flux will be equal to Vd star ODI minus Vdi. Similarly, we can rewrite this one as Vq ODI, and by substituting this results here. So, ID star we can rewrite, that is Fi ODI minus this one plus Kp this thing plus phi. Essentially it is integrating these voltages, thus this value becomes flux, since there is a integration involved. So, you are feeding voltage, essentially here you are getting a flux. So, this Ki Vi into Di essentially is the current. Similarly, this q axis current will be same, instead of the D it will have a q. So, here instead of the q here it will have a D, thereafter this proportional term, and thereafter this integral term, that is Ki Pv into phi Qi. So, where phi Di and the phi Qi are the auxiliary state variables of the PI controller in the controller in figure 3, and omega b is the normal angular frequency, and the parameters are shown in the figure 1 and 3. And now, let us see the current control block. So, you got the reference for the IQ ID axis, and you got a reference from the actual, you will compare it, then you put it to this actually the PI controller. Then you compare with the current through the inductor and multiply with the omega b into LFI, and ultimately this essentially gives you the voltage. So, you got a voltage. So, this voltage difference is Vd star. Similarly, IQ star you got, and ultimately you can feed it to this current controller, and thus you get the Vq star. So, general algebraic equations of the written controller are written as lambda di equal to IL di into IL di. So, if you differentiate it, similarly you got a essentially this value of q axis, and if you substitute it, that is the d axis inverter voltage, that is lambda d that is omega b LFI into LQI plus this current controller's PI controller term plus this one, since it is integrating the current. So, that will be a charge. So, into lambda into di, and where Vd and the Vq are the auxiliary state variable of the PI controller of the state variable 4, ILQI and ILQDI the direct and the quadrature axis component of the load current Li, and other parameters are shown in this figure. So, based on that we have a whole set of equations. So, these are the state variable, and ultimately we require to write the state space model. So, it is the di dt of dl of load current in d axis. So, you got this parameter, you can write in the observation, that is Rf by Lf, because you got a resistance into LDI with omega, there will be a q term IQ, and thereafter minus 1 by Lf into Vdi minus 1 by Li into Vo di. So, you can write it all those parameters. So, this is Vi, this is Vo di, and similarly in case of the IQ, just there will be a change in expression, there will be this two term will be minus, and instead of this Qi it will be di, and other terms will be almost the same. Thereafter, you write it for dV/dt also, that is essentially the current, and you get this equations, that is omega q I. Thereafter, that is for the d axis, similarly VO, this for the q axis. Thereafter, I 0, that is for the d axis, thereafter I 0 for the q axis. So, you have 6 equations. So, it will be, you will have a 6 by 6 matrix as a your state space for analyzing your voltage source, voltage control inverter, and thus you can write in a form of the state space equation. So, this 14 to 19 form a large signal dynamical model, and it is an average model, we have told it, that is ith dg. The large signal dynamic model can be written in a compact form, definitely, that is basically the fxi plus ki di plus gi, and of course, y equal to hi xx, where state vectors are phi I, pi, qi, di, and all those things, lambda. This is so you have a huge setup. We cannot use charge, integration of the current definitely gives you the charge, we use lambda because of the fact that we already use q as a reactive power. So, please keep in mind that we have used lambda for the charge and phi for the integration of the voltage, is the same for the flux, but we require to change, we cannot use q because we are using q for reactive power. So, the term di is omega com Vv di qi is considered as a disturbance, and the detailed expressions for fi, gi and ki can be extracted from the 1 to 21 whole equation we require to study, and the students are required to revisit the transfer functions, conversion from the state space to transfer function, then only they can realize the transfer functions of the system. So, the current control voltage source inverter, we now come to the another interesting topic. Previously, we had a voltage control voltage source inverter. Now, we will come across current control voltage source inverter. Of course, it will be in a it will be controlled in the DQ frame. It contains an inverter bridge, this one, connected to a primary DC source. It can be a solar cell or the fuel cell. The current controller adjusts the direct and the quadrature term of the output current IOI, as shown in the figure 6. A control block is used to calculate the angle of the ith CCVSI reference frame with respect to the common reference frame alpha I, such that the quadrature term of the output voltage VOQI becomes 0. This control block diagram is named as alpha I calculator. So, we shall see that how does it work. Ultimately, you have VDQ and VQ reference frame, you will sense the voltage, and thereafter you convert to this ABC to DQ frame, and it is the output voltage, and thus you transform into the your VD and VQ. Thereafter, you have an inner current control loop. So, you measure this IOI, then it convert to the DQ frame, you have IQ and DQ reference, and you have a VI. So, that reference is a modulating signal for this controller, and the block is named as a, now the second block, it is essentially your alpha I calculator. So, alpha I essentially is something like PLL. So, you require that theta. How does it work? You have VOI and you will convert to the VDQ to alpha beta to and they are at ABC frame, and you have a VQI, and once you have aligned your A phase with the D phase, then Q axis should be equal to 0, and thus it is compared with the 0 VQI. Then you fed to this PI controller, and definitely thereafter it becomes omega. This is a proportionality term. If you integrate omega, essentially it will become alpha, and that alpha or theta whatever may be the desired theta, and this is the PLL. It has been generated in this way for the current control voltage source inverter. Now, let us discuss the block diagram of the current control voltage source of the figure 7. So, you have ID reference and you have generated in fields referred to this block that you have this one. So, you fit to the PI controller, and thereafter you actually whatever the reference voltage you get, you then multiply with this omega B LFI and subtract VODL, ultimately you get the error. So, that will be your reference IDI, the reference modulation index or some that related to that parameter. And similarly, you have IQ refi and IQI, you subtract then KPCI plus KICI by S, now you multiply with omega B LFI. So, minus OBQI, and ultimately you get VIQI. The differential algebraic equations of the current controller is written as, so this is also the charge. So, that is lambda IDT equal to IDref minus IQ minus IODI. Similarly, here for Q axis it will be IQ ref di minus IQI. Mind it, there is a since there is a dimensional problem. So, it is an orientation. So, you should not confuse with the vectors. The current is not at all a vectors, and ultimately if you have integrated. So, in a d axis this is just a dq, just an orientation, it is not a vector. So, VIDI equal to VODI minus omega B LFI OQY plus the PI controllers and this value. Similarly, for the Q axis you got VOQY plus omega LFI, the cross product, that will be D plus KPCI VQ ref minus IQ ref plus this KICI lambda QI, where lambda di and the lambda QI are the auxiliary state variables for the PI controllers for the current control loop, and this figure 7 ODI and OQI the direct and the coordinate axis component of the output current IOI in the figure, and other parameters are shown in figure 1 and 7. So, now let us then again we have to write the state space modeling of it. Assume that inverter bridge produces the demanded voltage, that means that VDI equal to VD star equal to IDI and VIQI star equal to, so this referred parameter matches with that, and dynamic output voltage then it can be written as di dt, that will be this parameters, that is RFI by LF into ODI, this is a cross term omega m into IQY, thereafter 1 by LFI VQI and minus 1 by LFI VDY. Similarly, for the Q axis, so this term will be your D and other terms will be Q as it is. So, this is followed, but there will be a sign change for the Q axis. So, the equation 22-27 is a large signal dynamic model for the kth current control voltage source inverter. And so, you can rewrite in a short version, that is in a state space modeling, x dot CCI equal to FCCI, KCCI, DCCI, and these are your state variable, and this term is considered as a disturbance. These are your VDCOM and VODI, and then you can have a robustness studies, whatever studies you want, you do that in a, this is a control domain, and detailed expression of FCI, GCI and KKCI can be extracted from this two equation by writing this long form. Now, let us come to the point of control objective of the microgrid. The proper microgrid is a proper control of the microgrid is a prerequisite for the stable and the economic efficient operation. So, whatever state space you have, you should have a transfer function and you should have a stability study. And thus, instead of the mathematics, if you put in words, we should say those things here now. The principal roles of the microgrid's control structures are as follows. Voltage and the frequency regulation for both the operation modes, it is possible in voltage and current, voltage and frequency both to be controlled. Proper load sharing and coordination between different DGs, because one can be a source, otherwise another will be a load. So, this kind of problem will be there. Microgrid resynchronizations with the main grid if required, you are trying to dispatch power to the main grid, that is also possible. Power flow between the microgrids and the main grids and vice versa, optimizing the microgrid operating costs, proper handling of transient and restoration of the desired condition when switching between the different modes. So, these are the some criteria we wanted to get into it by this modeling. So, this requirement needs a hierarchical control structure and a different control hierarchy. So, this is a so you will have a territory control overhead, optimal operation in both operating mode, then power flow control in the grid tight mode, then you can have a second layer of operation, that is called a secondary control, compensating the voltage deviation caused by the primary control, compensating the frequency deviation caused by the primary control. Then primary control is these are the primary controls. So, voltage stability provisions, frequency stability provision, plug and play capability of the DGs. So, switch it off and switch it off as you wish, and circulating current avoid among the DGs. These are the primary control. So, accordingly we have a different task has been identified for the different people. So, this is the primary control that will be done with the inverter level. This is a secondary control, this is a task of all those things, and it is a tertiary control, mostly when it is connected to a dictate mode. Generally the grid operation will prevail and ultimately that will be their control. The microgrid's hierarchical control strategy consists of the three level, namely primary, secondary and the tertiary. The primary controls operates at the fastest time scale. So, it will operate quite fast and maintains the voltage and the frequency stability of the microgrid subsequent to the islanding operation when switching from the off grid to the connected mode. Now, what are the control objectives? It is essential to provide independent and active and reactive power sharing control for the DGs in the presence of both linear and the non-linear load. This is something we require to handle. Moreover, power sharing control avoids undesired circulating current. This is a primary control we have seen. Primary control level includes fundamental control hardware, control of hardware, commonly referred to as a 0 level, which comprises the internal voltage, current control loops and distributed generators. Secondary control mainly compensates the voltage and the frequency deviation caused by the operations of the primary control and restore the frequency and the voltage synchronization. And the highest level, that is the slowest time scale, the tertiary control manages the power flow between the microgrid and the main grid and facilitates an economical operation in this case. So, thank you for your operation. We shall continue with the microgrid modeling in your next class also.